Welcome back, quadrature fans. My name is Mary and Elena, and we're back teaching quadrature. Today, you guessed it, we want to really nail down the invariant. I think I misspelled it in the past lecture. So let's write it down. We want a good definition because definitions are key. And we're going to call this thing Iso Ratiometric Invariant. I misspelled it. It's a A. See that? Invariant. Okay. Iso ratiometric. Iso, that's from Greek, it means same. Ratio, well, ratio is A over B, something like that. That's a ratio. Metric, that comes from French, metre, it means measure. Measure, something like that. And of course, invariant, well, that's constant under change. Basically, that's our, this has a lot of meaning. Same, ratio, measure, constant under change. So let's go to it. Let's say we start out with our box as before, right? And we have a curve y equals x squared. Eventually we'll go y equals x third and x to the n. But for now, y equals x squared. And so that looks like this, and the setup, it helps to have a good setup. So you've seen this curve before. Y equals x squared. Here's our characteristic diagonal for the whole curve, and here's our curve itself. Oh, that's pretty, huh? I got good at it. After drawing it a lot of times. Oh, let's set us up. This is 0, A, 2A. Well, if this is a y equals x squared, okay, so this will be 0, this will be a squared, right? Plug in a, you get a squared. Over here, 2a, well, that's going to be 4a squared. I think we're set up. Okay, and essentially we are looking at, well, we're looking at this ratio of this slope, the tangent slope, to the characteristic diagonal of this box. So watch this. We have our box from 0 to a, and of course from 0 to a squared, because it's a x squared curve. And the things that we're looking at, two things. We're looking at slopes, but in particularly ratio of slopes. It's ratiometric. So this ratio of this slope to this characteristic diagonal, and we will prove that it really is the same as this slope here to this diagonal using rubber band geometry. We will also prove, to get my act together, the area ratio of this area to the box is the same as this area to this box. an interesting thing. Okay, let's just start out with this small box right here. And let's do some stretching, rubber band geometry, right? So what we do is we're going to take it like this from A, and we're going to stretch it to 2A. We're going to double it, right? So this box here, we simply grab and stretch. And we're going to get our diagonal, and it's going to look like this. Okay, 0A, 2A. So when we stretched it, well, what happened? Basically, we kept the height the same, but we changed the base, or the rise is the same, but the run has doubled. And so if you know that slope is rise over run, if I keep the height the same but I double the run, my slope has to be 1/2. This slope here compared to this slope has to be 1/2. It's shallow because I stretched it. And the same thing with this diagonal here. And compare this new diagonal, it will be more shallow. The slope will be 1/2 on this one, and this will be also 1/2 of this tangent. The ratio of the tangent to the diagonal is the same as the ratio here to here. That's unchanged. Now imagine that I stretch it now in the y direction, okay, and I pull it. Oh, I'm running out of ink. This is terrible.
There's another pen.
No, it just needs to be shaken. Okay, so basically you see that we're going to have to pull it 4 times, right? This is 1, 2, 3, 4. So if I do that, basically pull this all the way to the top, well, I get this. And it will look like, it's going to be that curve right there. Okay, you can see it. Something like that. Okay, so again, the ratio of this to the diagonal is the same as this to the diagonal, which is the same as this to this diagonal, right? It's the same thing. And the similar thing happens with the area. You know, here we started out, what did we do? Oops. We've doubled the area. When we go from here to here, if I stretch it from A to 2A, I've doubled the area. But I've also doubled the area of the box. So the ratio of this to the box is the same as the ratio of this area to this box. And if I now quadruple it, I pull it twice and twice again, well, we'll end up in this situation right here. So what have we done? Basically we have pulled this point to here. The slope what had happened to the slope. As we pulled to here, the slope became 1/2. And then we quadruple it, so it becomes 1/2 times 2, so it becomes times 2. So you can tell the relationship between the tangent here and the tangent here. That slope here has to be twice of this slope here. Can you see that? By rubber band geometry. Simply take it, pull it in the x, double it. Well, the slope becomes shallower, so the slope is 1/2 of this slope. But now, pull it 4 times, so that sharpens the slope, right? So 1/2 times 4 is 2. So this slope is twice of this slope here. But look at what happens to the area. You started out over here, and what happens to the area? The area is really 8 times. You can see 1, 2, 3, 4, 5, 6, 7, 8. These little boxes, there are 8 of them. The ratio of the area. We're on?
Yep.
Good. Okay. Wow, we got cut off by low battery. That happens. So where were we? Last time we compared the area in this little box to the area in this big box. And we said essentially that this, you multiply it by 8, gives you this. And we proved it by rubber band geometry, which you've seen rubber bands before. Here's a rubber band. What does it say? It says produit du Mexique asparagus. So that's from asparagus, and you stretch it, and the letters stretch in proportion. Rubber band. Now here's another rubber band, a fatter one. Look at that. Product of USA. What was this? Yeah, product of USA. And you, can you see this? Yeah, let's check it. If I stretch it,
Go up to the camera.
I hope it's in focus. See that? That's rubber band geometry. Everything stretches accordingly. Alright. So, this concept, we take it, we pull from A to 2A, and then of course from these A squared 4 times to here. Essentially we pulled this point to this point. And it's ratiometric and it's invariant. And what that means that there's, if it's iso, there's only one constant that describes this. One for area and there's one for slope. And we can call it K2 equals, well, it's the area of our little wedge. Okay. Compared to the area of the box. And of course the area of the, well, okay, and we'll call C2 is the ratio of the tangent slope, which we'll call M, M of our tangent, right, over the slope M the diagonal, characteristic diagonal. And if you want to know what the tangent slope is, well, simply C2 times M diag is the M tangent. Also, the area of our little wedge here, the parabola, underneath the parabola, is K2 times the area of the box. And it doesn't matter which box. So this gives you area equals K2 times the area of the box. Now what's the area of the box? Well, that's base times height, right? So we can think of it as base A times A squared. That'll be A times A squared. And so multiply, that's the area of this box, multiplied by K2, you get the area of this little wedge. Same thing happens here. That's the same as area, oh, excuse me, this is the little area. And the big area, of course, is base times the height times K2. So it would be 8 times, you got 2A times 4A squared times K2. So this would be area little, area big, K2 times 2A times 4A squared. And that's simply 8 A third K2. This is simply K2A A to the third K2, something like that, right? And you can see it's 8 times bigger. And the slope will be of the tangent, well, okay, M tan, the little one, little equals C2 times the slope of the diagonal. What's that? Well, it's A squared divided by A. That's your characteristic diagonal. That's the slope of this little guy. What about the slope over here in this big box? M tan big, again, C2, that's our invariant, ratiometric, times, what's the rise? In other words, what's the slope of this diagonal? That's 4A squared divided by 2A. And so that equals C2 times 2A, which is twice of the little guy. You can see that from here. Okay. All right, friends. So remember, before there was calculus, there was quadrature. See ya.